This example for sheaves is fox hunting. And I found this really cute fox picture, but we don't actually do real fox hunting in our family. We do hunting for radio transmitters. Okay, so let me show you what I mean. You can go to the GitHub repo kb1dds/foxsheaf, and you can find a paper in there that explains all this. But here's a picture out of that article. Here's our kid, Edwin, who is also a ham, and he's got a little ham radio hooked up to this antenna. And so what he could do is he could transmit, and then you could go find him. So it's a hide and go seek. Really, fox hunting is radio-based hide and go seek, where you hide a transmitter that could be automated or operated by a person, and you try to find the transmitter. And so what you do is you send out some kind of signal that tells the transmitter to respond to you. So when the transmitter hears a beep, it responds back with some kind of little signal that you can then trace. Okay, so as you're playing these games, the strategy changes based on whether you're far away or close to the fox. It varies based on the terrain. But as a simplified model, we're going to pretend that everything is just happening in 2 dimensions, first of all. The fox is just in 2 dimensions, and it's sending out some kind of pulse. And assume that some of these devices can only detect the angle to the fox. And that is kind of true in some situations. You can kind of get a sense in what direction you need to travel to get to the fox, but if you're like very far away or very close, and you can't travel a great distance while you're walking around, you may only be able to determine an angle. Sometimes you have to get in your car and drive several miles, and maybe you'll get a sense for whether you're getting closer or not. So it's a lot of fun. Anyway, so I'm going to allow the angle to be visible by this sensor and also sensor 3. All 3 of the other sensors, sensor 3, 4, and 2, though, are going to be able to tell volume. And it's in quotes because it's going to be some kind of signal strength measurement. It's going to be like the reciprocal of the distance squared or something like that. Okay, so this is going to be the volume essentially drops off as you get further and further away from the fox. Okay. So I happen to know where the sensors are, and that's okay. So these dark blue numbers I know. I'm going to secretly not know where the fox is. The fox is at 1, 1, and these other items are at other locations. Okay, so we know where the sensors are. We pretend we don't know where the fox is. We change X and Y, and now we have to figure out how to put functions on these arrows. Okay, so not to bore you too much, but to get the angle here, we just need some kind of arctan. We're going to use X and Y, and we're going to know these values because those values are known, but X and Y are just left as variables. So I'm going to need arctan over here again, and I'm going to need some kind of distance measurement on this distance measurement over here, but here I need the volume, which is a distance measurement, and arctan. So I'm going to use a NumPy array to hold that, because the way this thing is coded up, it can't hold more than one thing at a time. So if I want to have 2 pieces of information on these arrows, I'm going to have to use a NumPy to do it, a NumPy array to do it. And just as a matter of habit, you can just always use a NumPy array, even if it's only holding one thing. So anyway, you can usually get away with just putting, for these guys, you probably don't need a NumPy array. But if you just want to get in the habit, you can always use a NumPy array. Okay, so let's say, just assume we've got all those functions written out, which I have written out in the code, and let's see what happens there. Okay, and over here we have the same structure of the code we had before. We have the imports, we define our sheaf, we insist on an L2 norm, and we define the data dimensions appropriately. And again, the sensor 3 is different because it's taking in 2 different kinds of information. Now, we've got a problem here, and the problem is that we have 2 different kinds of measurements going on. So what I've done here is I've said, okay, oh, I guess I got rid of all my markings. My bad. Okay. So I have a distance measurement, and so I have a distance measurement here, here, and here, and I have an angular measurement here and here. And so they're kind of at odds with each other. So how do you want to weight that? You want to weight them equally? Do you want like 1 degree of difference to be the same as 1 unit of difference in volume? That doesn't make any sense. So I kind of bundled all of them together on one side. So let's say some angles and then some distances, and one of these guys gets a weight. And I forget which one I weighted, but that way you can control the ratio between the values you give to these two different things that are in here. So if you look over here in the code, I just call this weight 2, and then let's see where I put the weight on the angles. So the arctans have a weight associated with them, and then the other ones are just, you get what you get. So you can adjust the weight if you want the angles to be worth less than what they're currently defaulted to. You just drop the weight, and if you want it worth more, you increase the weight. And by doing that, you can have whatever ratio you want between those two types of distance measurements. Okay, and so that's the only thing that's kind of, I guess, different with this. The neat thing about this example is we do have two different things floating around here. Let's go ahead and see if it works. And I'm sorry last time I didn't give you the picture that I promised. PLT show. You know, oh, this is not too bad. Yeah, so the fox is in the middle pushing data out to the 4 sensors. That's pretty accurate. Okay, and let's see, the expected solution is at 1, 1. Our consistency radius did indeed drop. And where did it end up? It actually ended up very close to 1, 1. So I'm pretty happy with that. The consistency radius is reasonably close to 0. I'm pretty happy with that. So again, I can play around with this and see if I can knock it out of alignment, see how bad it has to get before I can't find the fox anymore. Like I might just see what happens if I make this weight very small and go ahead and run it and see if it can find the solution. And it did not find the fox. Okay, so what about if I made it go the other way? What if all the weight is over here? And well, it found the fox, I guess. Maybe it doesn't need anything else. Okay, but I could make the weight 1. So I can just play with that. Well, it found the weight it was better off with a higher weight over here. Maybe that's why I had it at 2. I don't remember. And then I'm just gonna go ahead and play down here. I can change whatever is going to eventually get optimized. So what is going to get optimized is the location of the fox. So I can start off, right now the fox is starting off at 10, 10. What if I started off really close to where it actually is and see how that changes my results? Okay, it looks like if I start closer to the fox, then I will end up closer to the fox in the end. And maybe if I start far, far away, I won't even be able to find the fox. So let's see. If I start far away from the fox, far, far away from the fox, maybe I won't even get there. Well, interesting. The x value wasn't so bad, but the y value was really bad. So I don't know. You can just play with that. Have fun with that. Let me just make the y value closer. Let's see if I can find the fox. Yeah, not good. Not good at all. Yeah. So you can just enjoy playing with these if you like and see how the system behaves for you. And there, we're back at the fox again. Okay, so that was hopefully a fun little example for you. And I guess moving right on to the next video.